the Pythagorean theorem with applications to special triangles. Let's assume that the triangle indicated is a right triangle. That is, this lower left angle is a right or 90-degree angle. Then we say that the two sides that make up the right angle are known as the legs, and the side which is across from the right angle, C, is called the hypotenuse. If that's the case, then the famous Pythagorean theorem is written simply as a squared plus b squared equals c squared. Let me say once more, it will only work if our triangle is a right triangle. All right, now let's do an example where I'll give some values. I've specified in this right triangle that A is equal to 2 and that B is equal to 1. And yet let's use the Pythagorean theorem to solve for side C, which is also known as a hypotenuse. So we have the formula A squared plus B squared equals C squared. Let's plug in these numbers. We would have 2 squared plus 1 squared equals C squared. That would be 4 plus 1 is equal to C squared. In other words, 5 equals C squared. Now to solve for 5, what we would do is take the square root on the right side and the left side. Now normally, when solving an algebraic equation, you would say that the answer was plus or minus. So this would be plus or minus square root of 5. But since we're talking about a physical situation here, that is a side of a triangle, we can't have a negative side. And so it's appropriate in this application to simply say that the answer is positive square root of 5. There are certain triangles that are used a lot in the study of trigonometry. One of them is the 45-45 90-degree triangle. Now we see here that the lower right-hand angle is our 90 degrees. If one of those acute angles, recall that an acute angle is an angle less than 90, so these other angles are both acute. Notice that if the one is 45, that the other one would also have to be 45. Why? Well, the angles in any triangle have to add up to 180 degrees. 45 plus 45 would give 90, and then the other 90 would give 180. So let's do an example here. Suppose that the hypotenuse is 1. Recall, hypotenuse is across from the right angle. And suppose that this leg down here is the square root of 2 over 2. All right, now if we're going to use the Pythagorean theorem to solve for the missing side, notice that C, the hypotenuse, is 1, and this leg down here could be labeled as either A or B. The legs are simply A and B in no particular order. So I could just as well have labeled that B. But since I labeled it A, then our unknown side is B. And what we would have is A squared plus B squared equals C squared. Now let's do the arithmetic. When I square that fraction, the square root of 2 times the square root of 2 is just 2. For the denominator, 2 times 2 is 4. 1 squared is just 1. Now, by the way, might as well go and reduce that 2 fourths. 2 fourths could certainly just be reduced to 1/2. So let me get rid of that and I'll reduce it. Okay. All right, now to solve for b squared, we'd have to take 1 and subtract the 1/2. Well, 1 is the same as 2 halves, so 2 halves minus 1/2 would just be 1/2. And we would finish this off by taking the square root of the left-hand side, which would be b, and the square root of the right-hand side, which would be 1 that is the square root of 1/2. Now I'm going to essentially simplify that, that radical that we see. We're able to rationalize the denominator. So a little bit of review algebra here. When you have a fraction under a radical, you can break it up into like this, the square root of 1 over the square root of 2. Now that, of course, just equals 1 over the square root of 2. And then let me remind you that we normally rationalize denominators. That is, when we have a radical in the bottom, we normally eliminate it. It's very easy to do. We have that square root of 2 down there we want to get rid of. Multiplying by the square root of 2 will get rid of the radical sign, as I'll show in just a second. Now whatever you do on the bottom, you have to do on the top. So this gives us square root of 2. But notice the bottom. Square root of 2 times square root of 2 is square root of 4. But square root of 4 is just 2. And so this would be our simplified answer for that problem. You'll be seeing this particular triangle, the values in it, come up again later on when we look at trigonometry. My last example in this lesson is a 30, 60, 90 degree triangle. Now, obviously we have a right angle there. And notice, the angles have to add up to 180, so this angle I didn't specify certainly has to be 60. 60 plus 30 plus 90 gives 180. For this example, I again would like to imagine that the hypotenuse is equal to 1 and that the side or leg over here is equal to 1/2. Alright, well, a squared plus b squared is c squared, the familiar by now Pythagorean theorem. We know that the hypotenuse is always indicated by the letter C. The two legs are interchangeably A and B, so I could call the one down here A and the 1/2 B, or I could label them vice versa. Let's put in the values. Right, we don't know A, so it's still just A squared. B is 1/2, and C is 1. Now that would be A squared plus 1/2 times 1/2 is 1/4. And 1 squared is just 1. I subtract 1/4 from both sides, and on the right hand side I get 1 minus 1/4. Well, keep in mind 1 is the same as 4 over 4. So 4 over 4 minus 1 over 4 would be 3 over 4. So let's take the square root of the left-hand side, a squared, and the square root of the right-hand side. When we take the square root of a squared, it just gets us down to a, which is what we want. The right-hand side would be the square root of 3 over the square root of 4, or rather over 4. But I kind of anticipated what I'm going to show you next. Just as in the last example, we'll break up that radical, square root of 3 over square root of 4. And notice that the bottom will just naturally turn out to be 2. The square root of 4 is 2. So we're good. We don't have a radical in the bottom, and we're done. All right, that ends this lesson. Good luck.